discussion, we'll introduce the topic of implicit differentiation. Up until now, when we've differentiated a function like, say, y equals sine of x that is explicitly defined. Sometimes, however, a function is defined implicitly. For instance, even this simple function, if we subtract sine of x from both sides, this is less explicit what y depends upon in this statement than it is in this statement. So in this discussion, we will learn to differentiate when a function is less explicit. For example, let's look at this example here. Even though we do not have this expressed as a function of y, it can be differentiated using an application of the chain rule. What we do is we differentiate almost like normal, using the power rule here, using the power rule here, using the product rule here, treating maybe 6 as just a constant, but x is one function and y is the other. But wherever y is involved, we think of y as a function, and so we use the, it's sort of like we have a composition function here. We have a function being cubed, and cubing something is a function in itself, so we'll apply the chain rule. In practical terms, it's a very simple thing. We'll differentiate this normally, you get 3x squared. We differentiate this normally to get 3y squared, but anytime you differentiated a term that had a y in it, we throw in a dy dx. That's an application of the chain rule. We're taking the derivative of the inside function, the y. Or we could use the y prime symbol here. Now on the other side of the equal mark, in this particular example, like I said before, we need to use the product rule. So we'll take 6x and multiply it by the derivative of y. Well, the derivative of y is just 1, but remember, anytime we differentiate a y term, we'll throw in a dy dx when we're using implicit differentiation. And then it's plus the second function, y, times the derivative of the first function. Well, the derivative of 6x is just 6. Cleaning this up a little bit, I have 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y. Now, our goal is to differentiate. That means we'd like to know what the derivative of y with respect to x equals. So in other words, at this point, we're solving for the dy dx. So I will get all of the terms that have a differential of y with respect to x on one side of the equation. And the other terms on the other side. We can't add these up because, of course, 6x and 3y squared are different terms, but we can factor out a dy dx so that we have 3y squared minus 6x times the differential of y with respect to x. The relationship here is multiplication, so we will divide both sides. And so we have the derivative of y with respect to x is equal to 6y minus 3x squared divided by 3y squared minus 6x. And we have found an expression. It's not solved for y, but we still have an expression for the derivative of y with respect to x. And that's an example of implicit differentiation.